In this video, we're going to be taking channel packing to the next level. Let's go. Channel packing means placing multiple grayscale texture images together in the channels of a single texture. We do this to reduce the total number of textures sampled in the shader and to reduce the texture memory we use. In this video, I'm assuming you already know how to do that. If you don't know the basics, I've linked a great video series in the description. So go ahead and take a look at those videos first. So using standard channel packing, we end up with a set of 3 textures that look like this. We have our color texture, our normal map, and a mask texture with 3 or 4 masks all packed together. That's pretty efficient, right? We only have 3 textures with as many as 7 maps all packed up. So here we have our color texture with optional opacity. We have our normal map with XYZ, and we're not using the alpha channel of the normal map. And then in our mask texture, we have our ambient occlusion, our smoothness, or our roughness, depending on which engine we're using. And we have our metallic mask, and we have our height. So this is a pretty typical way of packing textures. And this scheme covers pretty much every type of 3D asset, but it's a little bit wasteful. What if I told you we could get this 3 texture scheme down to just 2 textures for some types of assets? Let's take a look at how we can do that. So for a lot of assets, we don't need our opacity texture. And here in the normal map, it's possible to store a normal with just the X and Y data and not use the Z data. We can calculate the Z data later based on the X and Y. And then also, we're not using the alpha channel as well. Now, in some types of assets like foliage and vegetation, terrain and rocks, we don't need a metallic mask. So if we're storing this blue texture just as black, we're also wasting that channel. And then for a lot of asset types like foliage and rocks, we don't have any need for a height map. So if we take a look at what we've got here, we have 3 textures, which adds up to a total of 12 channels, but we're only using 7 of them, and 5 of them are going unused. So almost half of the potential is unused here. And so what we need to do is rejigger this just a little bit so that we can get this from 3 textures down to 2. So let's take a look at how that can be done. So here's our advanced channel packing scheme. We have our color texture, and in the alpha channel, we're going to put the smoothness or the roughness data. Then we have our normal map, and notice now that we're only storing the X and Y of the normal, but in the blue channel, we have our ambient occlusion or our opacity map. And then in the alpha channel, we have our height. Now, in some cases, we don't need height, and so it's optional to store this value. And what that allows us to do is to eliminate our mask texture because we're storing everything that used to be in the mask texture here in the blue and alpha channels of our normal map, and also the alpha channel of our color texture. So for some types of assets, we've been able to eliminate our 3rd map and get this down to just 2 textures. So now we're using less memory and doing fewer texture samples. If reducing the amount of resources you're using and making the shaders perform as fast as possible is important, then this technique should definitely be used. If you're always using the 3 texture method for all asset types, then you're leaving memory and performance on the table. And I think it's worth it to make texture packing schemes that are unique to the needs of each individual asset type, rather than only using one universal technique for everything. So the next thing that I need to do is show you how to handle the normal map here. Because once you put other data into some of the channels of your normal map, you can't tell the engine anymore that it's a normal map. And if you do that, then the things that the engine does under the hood to handle normal maps, it's no longer doing. So you have to do them yourself. So next I'm going to show you how to do that, as well as how to automatically compute the Z component of the normal from the X and the Y components. All right, here we are back in Unreal, and you can see that I've got my standard 3 texture packing scheme happening here. I have my base color texture, and it's plugged into base color. I have my normal map, and it's plugged into normal. And I have my mask map, and you can see that my red channel is plugged into ambient occlusion, and my green channel is plugged into roughness, and I've got my metalness in the blue channel, and I have my height in the alpha, but obviously I don't need to plug that into the root. So this is how we typically texture objects, with these 3 individual channels, and this is pretty efficient. Like I said, we're only using 3 textures, but in some cases we can get this further. We can go down to 2. And so over here, I've created these 2 textures. And what I want to do now is show you how these 2 textures are just a little bit different than these 3. First of all, I've got my color texture here. And if we take a look at the texture, you can see that in the alpha channel, I have the roughness map stored here. And storing the roughness map in the alpha channel of the color means that I don't have to store it in an additional 3rd mask texture. Okay, now let's take a look at my normal map. And in this case, I've called my normal map NOH, which means that in the red and green, I have the X and Y of the normal. In the blue, I have the occlusion. And in the alpha channel, I have the height. So let's take a look at that. So here's my X and my Y for the normal. Here's my ambient occlusion in the blue, and here is my height data stored in the alpha channel. Now, one thing that's important to notice here, if we take a look at a standard normal map, for a standard normal map, we have the compression settings set to normal map, right? But for an NOH texture, we can't save it as a normal map because it has this extra data stored with it. And so I've set my compression settings to BC7 instead. Now, normal maps are always stored with sRGB set to off. So make sure that when you bring in this texture, you turn sRGB off and you set your compression settings to BC7. You might be tempted to set this to a normal map, but if you'll do that, you'll lose some of the data that's in the other channels. So you're going to set compression settings to BC7 and sRGB to off. So if we come back here to our shader, you'll notice that when we bring in our adjusted normal map, our cobblestones NOH, that it looks really different here in the preview. And the reason for that is because this texture sample, because we've set it as a normal map, Unreal and Unity are automatically doing some things under the hood to change this data from a texture to a vector. And the way that that works, I'm just going to move this over to give myself some more space. What this is doing is the data is stored in the range of 0 to 1. And vectors are stored in the range of -1 to 1. And so when you tell a texture that it's a normal map, the engine is going to automatically expand that range for you. But because we haven't done that in this texture, it's not automatically expanded. And so we have to do that ourselves. Now remember, the other thing that I told you that we needed to do is calculate the Z component of our normal, because in this case, we've stored the occlusion in our blue channel instead of the Z component. Let's take a look at that really quick. Here's my regular normal map. And in the blue channel, this is the Z data. But in my NOH map, if we take a look at this, this is our occlusion data. Now, the two of these look similar, but they're not exactly the same. This is our ambient occlusion, and this is what our Z data looks like. So what we need to do is do some math to compute this Z data based on the X and Y. There's a mathematician that lived a really long time ago in ancient Greece, and his name was Pythagoras. And you may have heard of him. He came up with something that's called the Pythagorean theorem, and that is for a right triangle, you can find the measure of the length of one of its sides if you take the squares of the other two sides and add them together. That will be the square of the third side. And so that's what we're going to do right now. What we need to do is we know X and Y, and we need to figure out Z. And so we're going to use the Pythagorean theorem. And I know that sounds kind of fancy, but it's really not that hard. These are the nodes that we're going to use down here. I've got them set up already. So what I'm going to do is I'm going to take my X and my Y of my normal. And then just like I said before, I'm going to expand them by multiplying by 2 and then subtracting 1. So once I've done this, you can see that my original data looks something like this. And then I multiply it by 2 and subtract 1, and now it's kind of like increasing the contrast of it, but it forces some of the data into the negative range. So I'm expanding my range from 0 to 1 to negative 1 to 1. All right, so there's my X and my Y with my range expanded. Now the next thing that I need to do is multiply both X and Y by themselves. So I'm taking X and Y, and you can see I've got it plugged here into the A and the B. So I'm basically squaring both my X and my Y. Then I take my X data and I do a 1 minus that, and then I take my Y data and I subtract it from X, and then I find the square root of the result. And the end result looks something like this. Right? And then so this is the Z data that I was looking for, and I can compute it just by squaring it and then 1 minusing the X and subtracting that from Y, and then I get my result. So it's pretty simple. That's all the math that you have to do to convert the X and Y of a normal into the X, Y, and Z. Then I append it here with the original X and Y. So now the result of this append is the X, Y, and Z of my normal. And if you look at our preview, now our data looks exactly like our original normal map, as if I had stored X and Y and Z together. So let's take a look at the difference. Right now I've got my 3-channel data, or my 3 texture data plugged into the root. I'm just going to temporarily delete this connection so you can see what these normals look like. And if I plugged in this computed normal map instead, you can see that the result is exactly the same. So I've been able to take this normal that I've stored in 3 channels and just store it in 2 channels. Pretty cool. All right, I hope you like that trick. So let's replace our 3 channels here, or our 3 textures here, with just 2. I'm going to take the color and plug that into base color. I'm going to take the roughness that I stored in the alpha channel and plug it into roughness. I've already replaced my normal here with the normal there. And now I'm going to take my ambient occlusion that I stored in the blue channel and plug it in. And now I don't need height either. So we've replaced our 3 textures with 2, and I'm getting exactly the same result. Now there is one small difference that I want to take a minute to show you and just warn you against this. So if you see it, you'll understand why it's happening. I'm going to switch over to our NOH normal map texture and turn on the red, green, and blue channels. And I'm just going to zoom in here to, let's zoom into 400%. I just want to take a look down here in the bottom right corner. So let's take a look at that normal map like that. And then I'm going to switch to my regular normal map that I'm just storing the conventional way using normal map compression. We're going to zoom into that one with 400% as well. Using normal map compression, if you take a look at my texture here, it looks almost as if I was storing it uncompressed. The data is completely smooth. But if I take a look at my NOH version, what you can notice, and I'm not sure if this is going to come across with the YouTube compression and such, what you might notice is that there are a little bit of blocky artifacts going on here. Can you see that? Just a little bit of blockiness. Let's switch over to just the blue channel. I'm going to see if I can find one of the three channels that maybe shows a little more blockiness. Yeah, maybe this red channel. Can you see how it looks like there's a little bit of a grid happening here? Maybe in the green channel as well. That blockiness is happening because when we use BC7, the texture compression impacts our normals a little bit more. When we tell the engine that we're compressing this as a normal map, it uses a compression scheme that's specifically designed for normals. But when we don't use it, when we just use BC7 instead of the normal map compression scheme, our normals get impacted just a little bit. There's just a little bit of quality loss there. And so the trick with using this two texture packing technique is to know when you can use it, when it doesn't matter that quality is getting lost. And let me give you some examples. This is a good technique to use for vegetation and foliage because your normals don't need to be precise. And the main thing that you see with vegetation and foliage is the really interesting shapes that the opacity cutouts give you. And so foliage and vegetation is a good opportunity to just use a two texture packing scheme. Another opportunity is with rocks. Rocks can use two textures because the normals don't need to be quite as precise. They're mostly just noisy. And chances are you're going to have a detail normal on top of your base normal anyway, which is giving you most of the detail. And that can be stored as a normal map. And so you don't see the quality loss there either. Another example, and I already showed this a long time ago in a previous video, is on terrain textures. On terrain textures, it's really important that we use as few texture samples as possible. And so using this technique is a good idea there as well. Number one, because it's going to save performance because you're already sampling a lot of textures on your terrain. And number two, because a lot of times terrain is covered up by detail meshes, by grass and weeds and little rocks and things. And so you don't notice the details on terrain as well. Now, there are a couple of cases where using the three texture packing scheme is going to be better, especially in cases like your characters, character faces, for example, where you need really precise normal maps. That's important to use or to not use this extra compression or extra packing that we're using to get things down to two textures. Another example is hard surface mechanical objects where the precision of the normal map is really important. And in those cases, you're going to see the problems or the quality loss that you get with the normal map if you use this packing scheme where you're putting other data in with your normal map. There's one more thing that I want to show you, and that is we're doing a little bit of math here by multiplying the x and y by themselves, and then subtracting, and square root. And there is a node that actually does all of this, and it's called derived normal z. And so I'm going to grab my derived normal z node, and now I can just take my x and y, multiply by 2, subtract 1, and then plug it directly into derived normal z, and then plug that into my normal. And now you can see I'm getting the same result using this node as I got from using all of these. So if you want a little bit cleaner shader, go ahead and use derived normal z, and you won't need to use all of these nodes like this. But it was important for me to show you exactly how this math works to go ahead and compute the z component of the normal from the x and y, and that's what this node does. So I'm just going to go ahead and delete these, and now I have a nice clean shader where I'm converting this x and y data stored in my red and green channels into complete normal. All right, let's jump over to Unity, and I'll show you how to do the same thing there. In Unity, I have my same 3 textures that I brought in. I have my color texture, my normal map, and my mask map texture. And you can see that I've got all of those plugged into the master stack. And I also have the version of the material that just uses 2 textures. I have my color and my roughness. And in this case, I need to bring it in as color and smoothness because Unity uses smoothness instead. And I also have my normal, occlusion, and height texture. So in this case, I need to unpack my normal, occlusion, and height texture to create my correct normal from my X and my Y data. So I'm going to open up this node here and come down here to the bottom. I'm going to plug my RGBA texture here into this swizzle node. And the swizzle node is just taking the RGBA and isolating just the X and the Y components, just the first 2 channels. So you'll notice it changes from pink, which is the vector 4 or the 4-channel data, to green, which is the 2-channel. Now I need to expand this data from 0 to 1 to the -1 to 1 range. And in Unity, I can use this node called remap. And so what I do is I tell it that this data coming in starts out in the 0 to 1 range, and I want to expand it to the -1 to 1 range. So in Unreal, in order to do this, I use the multiply by 2 and then the subtract 1. But in Unity, I have this convenient node called remap, which is basically doing the same thing, but I can just tell it my starting range and my ending range. And then, just like in Unreal where we used the derived normal z node, Unity has this node called normal reconstruct z, where we plug in our expanded X and Y data, and what it gives us as a result is the X, Y, and Z data. So just like we did in Unreal where we were manually computing the Z, this node is computing that Z and creating our normal. So now you can see that the normal that we've created looks exactly like the normal that we got as if we had had that Z data there the whole time. So I can go ahead and plug all of these in. So right now I'm getting a preview result that looks like this. I'll go ahead and plug in my normal here to replace that. I'll plug in my color here to replace that. I'll plug in my smoothness to replace that. Now I have my ambient occlusion that's coming from here, and we're not using assets that need the metallic, and so I can get rid of that. So now, just like I did in Unreal, I have replaced our 3 texture scheme with a 2 texture scheme. All right, so that about wraps it up for our video today. I hope you enjoyed it and that you learned that it's possible to pack things much more efficiently. This is a pretty cool technique where you can reduce your texture memory and your texture samples from 3 down to 2 in specific cases like foliage, rocks, terrain. There may be some other cases as well. You don't want to use this where you need really precise normals, but where you don't, you can save some performance and memory by packing things into 2 textures instead of 3. All right, everybody, have a great week, and be sure to come back next week for some more shader goodness on the channel. If you liked the video, please give it a thumbs up, and let me know down in the comments if you have any questions about this technique, or if you have some ideas for what you'd like to see next week. Thanks a lot.